Hello and welcome in the 10th lecture in the course two-phase flow and heat transfer. In this lecture, we will be giving you idea about measurement techniques in two-phase flow and how the signals obtained from the measurements can be analyzed. Now, in this lecture, we are having two parts which we will be also continuing in the next one, that means the 11th one. So, here I will be discussing the first part only. So, at the end of this lecture, we will understand different measurement techniques in two-phase flow based on lag between information transfer at interface. So, as it is two-phase, both the fluids will be having different properties to transfer the information through it. Depending on that, we are devising different measurement techniques. So, we will be discussing about those. We will be discussing about the difference between analog and digital signal analysis. So, how primitive analog signal analysis and at present modern digital signal analysis differ in principle, those things we will be discussing. We will be also giving you idea about electrical conductivity probe and optical probe. We will be also showing you that how signal analysis from this conductivity and optical probe can be done via probability density function and wavelet analysis. Okay. Now, to begin with, let us see what are the different principal sensing method are available in two-phase flow. So, what we will be doing for measurement of two-phase flow, we will be exploiting any property, okay, which is significantly different for the phases. Okay. So, let us say we are taking two phases as gas and liquid. So, we can take any fluid property or exploit any fluid property, okay, which will be behaving differently amongst these gas and liquid phases. Okay. For example, here I have named few technologies. For example, let us say let us see this right hand side first, flow rate, pressure and temperature. So, here you will be finding out for a given pump the flow rate for the gaseous phase and liquid phases will be different, because their fluid properties like viscosity, density, those are different. So, obviously, you will be finding out for a given input the flow rates for both the phases will be different. So, by knowing the or by calibrating those flow rates beforehand and later on for some unknown flow rate, we can find out what phase is going on inside the pipeline. Okay. In a similar fashion, pressure drop, okay, and temperature also can be utilized for sensing the flow characteristics inside the pipeline. Now, let us see some modern techniques. So, in the left hand side I have shown electrical conductivity, capacitance, optical. These are also different methodologies using which you can measure the two phase parameters. For example, conductivity, this is electrical conductivity. So, gas phase and liquid phase, they are having different electrical conductivities. So, if we pass electricity between the two phase mixture, depending on the presence of gaseous phase in the liquid, you will be finding out that signal is differing. Okay. So, using the electrical conductivity of the medium where both the phases can be present, we will be finding out the two phase measurements. So, that type of technique is called electric conductivity measurement. In a similar fashion, if you use capacitance principle of the fluids, okay, we know that capacitance of gaseous phase and liquid phase will be different. So, depending on the capacitance property, if we define or if we describe some probes, okay, which will be picking up the information of capacitance in the two phase flow, we will be finding out that it can measure the two phase parameters. Similarly, optical parameters. So, light will not be passing in a similar way in gas and liquid. So, you will be finding out that depending on the attenuation, okay, there will be lots of differences at the interface. So, in presence of interface can be found out whenever optical ray is passing and attenuating from the interface. Obviously, optical can be used for photographic purpose also. Using normal camera, we can take a photograph if the pipe is see through, and we can find out what different type of two phase flow is occurring inside, right. Few modern technologies are also like this: X-ray, gamma ray, neutron and radio frequency. So, both the phases are behaving differently in the presence of X-ray, gamma ray, neutron and radio frequency. So, depending on these principles also probes can be developed. Okay. So, nowadays advanced researches are going on for development of X-ray, gamma ray, neutron ray and radio frequency probes. We can use ultrasonic property. So, sound speeds are not same in liquid phase and gaseous phase. So, depending on the sound speed also we can generate some amount of probe. So, ultrasonic probes are also very popular for measurement of two phase flow. Magnetic field also behaves differently in both the phases. So, we can develop magnetic resonance probes, okay, for measurement of two phase parameters. And we can also see chemical and electrochemical behaviors of the phases. Let us say we are going for some chemical reactions. Now, that chemical reaction will be enhanced if the substances are in liquid phase, and it will not be that much active if the substances are in gaseous phase. So, obviously, you will find out that depending on the chemical and electrochemical potential, the fluid can be identified. Okay. So, all these techniques nowadays people are using for measurement of two phase flow. Now, first I will be showing you for measurement of two phase flow what is the most primitive technique. Okay. Primitive means quick, and many a times we use in our lab. So, what we can find out, let us say here I have given one idea or schematic of the tube inside which we are having two phase. Here the white colored circles are resembling, let us say, the gaseous phase, and the black colored background is showing you the liquid phase, right. So, eventually you can consider that inside a pipe we are having bubbly flow. Now, what we will be doing for measurement of void fraction, we will be having two quick closing valves over here. Okay. So, in the general conditions, the valves will be open, so that flow can be there inside the pipeline, okay, without disturbing the void fractions. Now, what we can do, as we are using quick closing valve, quickly both the valves will be closed simultaneously. So, in that way you will be entrapping some amount of two phase mixture in the intermediate pipelines. Okay. Now, we know that both the phases are behaving differently in the presence of gravity. So, gas will be moving up and liquid will be falling down. So, you will be finding out that after some time we are having some stratified layer of liquid and gas over here. So, if you just measure the length of these two, then you will be finding out volumetrically what is their ratio, and once you know the volumetric ratio for a constant diameter pipeline, finding out void fraction is not difficult. Okay. So, this is a primitive methodology, or not primitive methodology, I should say, this still we are using. This is not that much accurate. So, it is associated with error, because you will be having manual error whenever you will be closing the valves. Okay. But this still we are using for quick measurement of void fraction. Okay. Then let us try to see that nowadays whatever probes or sensors we are using, those are having two different dimensions. Okay. First dimension is that we are having analog type, okay, and another one is digital type. So, let us try to understand what are these two modes, analog mode and digital mode. So, what I have given you over here, a figure which shows you circuit for analog signal processing. Okay. So, essentially this is a pipe. So, you can see this is a pipe carrying some flow. This can be single phase flow also or two phase flow, depending on the flow configuration. I have given the example using single phase flow, and it is somehow is having a venturi. So, some restricted flow path is there. Okay. So, now what you can find out, if we tap the liquid from the smaller cross section portion and from the pipe, then we can connect those two taps around a piston. So, this is a piston. So, you can find out it is connected in the upper side, this is connected in the lower side. Okay. Now, depending on the pressure drop here and here, you will be finding out that the piston is moving up and down. Right. So, depending on the flow velocity, you will be finding out the pressure drop between these 2 points are varying, and as a result you will be finding out the piston is moving up and down. Okay. So, this piston movement can be correlated with the velocity of the pipe. Right. Now, as we are having this piston movement, that can be easily converted to a stylus movement via some weight floating on the liquid, and you see here we are having a ball valve, and that ball valve is connected with a stylus. So, that means if you are having reciprocating motion over here, this blob will be actually moving, as a result the ball valve will be also moving, and the stylus which is connected with this ball valve will be also moving like that. Now, if this stylus is actually placed against one graph paper, okay, or you can say some sheet, then you will be finding out that this reciprocation of the piston can be represented in the graph paper. That means the velocity fluctuation in the pipeline can be represented here in the sheet or graph paper. So, this was the earlier methodology of obtaining signals for some variable input. Here the velocity was the variable input, and that has been obtained in the graph paper, right. But what happens here, I have given you some sort of idea of analog system. So, here you see this is for two phase flow, here we are having gaseous bubble in the periphery of liquid. So, this is the sensing element. So, this is sensing something. So, here we have given strain gauge pressure transducer, okay, which will be sensing and it will be giving some signal. So, then we are having some processing circuit over here. This processing circuit can be any mechanical arrangement. Here the mechanical arrangement was this piston cylinder device. Okay. After that it will be giving signal to some magnetic oscillograph with inking brush. Okay. So, this is the magnetic oscillograph with inking brush. In our previous figure that was replaced by a stylus and the paper. Okay. And finally, from this graph paper we need to find out some information. So, what we do, we use some polar planimeter and manual counting. So, if you have the graph paper, you can count how many peaks and valleys we are having in the fluctuations of the graph paper manually to get some information, or you can use a polar planimeter which will be giving you that what is the area under the graph, okay, and that can give you some sort of information. So, this was the typical analog system used earlier. Here I have shown you one old experiment. Okay. So, here you see this was experiment of reweighting. So, this was a heated rod, around that we have actually sprayed liquid. So, let us say you have a heated rod and you have sprayed liquid from surroundings. So, you will be finding out that first that liquid will be flooding the this heated rod, and after certain period when boiling will be starting, you will find out that the liquid is jumping from the solid heated wire. Okay. So, that is actually called reweighting. Reweighting, why? Because after jumping once again it will be touching. So, in between some portion it will not be touching the heated rod. So, here we have shown the propagation of reweighting front, okay, using our analog signal. So, this is once again the stylus recording on a graph paper. So, you can find out over here that from here to here we are having actually no contact between the liquid front and the heated wire. Okay. Now, as time progresses you can find out, so here you can find out that here we have given two signals like this, two different conditions. You can find out that the area under this peak and valley curve is reducing. That means at two different conditions, whenever our heater rod is having two different temperatures, we can find out that what is the heater temperature by comparing these two graphs. So, obviously this is having low temperature of the heater rod, this is having higher temperature of the heater rod. Okay. So, this kind of comparative graphs earlier people used to make. Okay. Next, let us see the modern technology. Nowadays whatever we are using, that is called digital system. So, here in this digital system sensing element remains same. Okay. Those works on the principle of difference in thermodynamic or fluid mechanics properties, as I have mentioned in the previous slides, different properties we can use. So, sensing element remains same. So, you see this is the sensor. Okay. And after that we are having processing circuitry also. Earlier that was, in case of analog, that was mechanical processing circuitry. Nowadays we are converting that one into digital processing circuitry. Okay. So, these are actually electronic processing circuitry. Then after that we are having a data acquisition system. These data acquisition systems are having typically few features. For example, it will be for storing, then it will be actually filtering, then it will be amplifying, and lots of post processing also we can do using this type of data acquisition system. And finally, the data acquisition system will be sending the signal to store in a computer. Okay. So, these are typical components of a digital system whatever we are having now. Now, for signal conditioning, so here in data acquisition system we have signal conditioning, as I have already told you. It will be handling amplification, it will be handling filtering. If you have some unwanted data, raw data from noise, those it will be filtering. Okay. It can also do multiplexing, that means let us say you are having multiple probes and data are coming from those multiple probes. So, what you can do, those data you can club in a single channel and you can do some subtraction, multiplication or addition. So, those are called multiplexing. So, using this data acquisition system you can also do multiplexing, right. And at the end you can go for some compensation. We know that for some sensing element like thermocouple temperature measurement device, we have to go for compensation. For thermocouple typically that is called cold junction compensation. So, using this data acquisition system we can do those compensations electronically. Okay. In case of analog, those compensations needs to be done manually, right. Okay. And after this data acquisition system in the computer, we can go for signal processing, feature extraction and then qualitative information and subsequently quantitative estimations. So, after we get the signal, it is very easy to do the post processings, okay, and obtain some sort of quantitative as well as qualitative informations. Okay. Next, let us try to see that how we are obtaining these informations, quantitative and qualitative informations. So, we have to go for techniques, different techniques for signal analysis. Now, these signals can be of two different types. If you are taking the signal using a camera, the signal will be coming in the form of image, pixelated image. So, we can have image processing techniques. Okay. From image we can extract some amount of information. On the other hand, some probes are there which will be giving us the electrical signal. So, we can have techniques for signal processing also. Let us go through what are the techniques for image processing. For example, first one is edge detection. As you are having let us say interfacial configuration and you are taking a photograph. So, first task is to find out where is the interface. So, you can do edge detection. Edge detection means you can typically identify where liquid is and where gas is, and the intermediate thing is actually the interface or edge, right. So, you can go for edge detection and find out the interface. Similarly, we can go for pattern recognition, cross correlation, auto correlation and some modern day fuzzy logic based technique also using image, right. So, this cross correlation, auto correlation and fuzzy logic, those are mathematics based topics. We are not going into detail of this one, but nowadays tools are available with cameras using which you can go for cross correlation, auto correlation and fuzzy logic based treatments. Okay. Now, for signal analysis, electrical signal analysis, first one obviously we can see the raw signal which is called visual inspection. So, from visual inspection you can find out that if you are getting some features or not. Then quickly next we can go for probability density function for the signal. Okay. I will be showing you some signals over here with probability density function. You can go for power spectrum density function, PSDF. So, PSDF is once again a mathematical tool using which you can analyze some time data. Okay. You can go for fast Fourier transformation FFT, okay, or STFT. Okay. We can go for wavelet analysis also. I will be showing you what is wavelet analysis. And some typical signal analysis processes like cross correlation, auto correlation, fractal analysis, chaotic analysis, neural network and complex network. Some of these I will be telling you in the next lecture. Okay. So, first example we will be taking is a gas liquid upflow through concentric annulus. Okay. So, let us say you have a annulus section where gas and liquid is flowing in the upward direction. Okay. So, it is not a pipe, it is actually one annular section. So, inside a pipe you are having a solid concentric tube. Okay. So, the gas and liquid can only flow in the annular region. Okay. So, here in this experiment what we have done, we have used parallel plate conductivity probe. Okay. So, electrical conductivity probe, parallel plate electrical conductivity probe as sensor, and for characteristics analysis we have gone for signal analysis through PDF. Okay. So, this is typically a single sensor single feature application. Okay. So, let us see what are the different types of conductivity probe, electrical conductivity probes are available. So, first here you see we are having parallel wear conductivity probe. So, this is a cross section of the pipeline. So, what we do, we make holes like this, okay, face to face holes like this, okay, and we pass electrical wear. So, this can be copper wear or this can be aluminum wear, okay. So, through which we can pass electricity. So, what we will be doing, one side of this wire we will be bluntly fixing in the pipeline, and other side we will be taking out, okay, and these two we will be connecting with the some power supply. Now, depending on the medium present in between, okay, as these two sides are not connected, okay, so these are bluntly fixed with the pipe wall. So, there is no physical connection between these wires, okay, only connection between these wires are through the medium, okay, in between the wires. So, depending on the medium whatever you have, the circuit will be closed and resistance, overall resistance will be determined, okay. If we are having air in between these two wires, so you will be finding out that we are having a huge resistance in the circuit, and if you are having some liquid, let us say water over here connecting this to wire, then you will be finding out that there is a very less amount of resistance, okay. Now, if we try to give a constant voltage over here, okay, and if we try to find out that what is the voltage across some small section using one voltmeter, then we will be finding out that depending on the medium inside the pipeline, the voltage is actually fluctuating, right. In a similar fashion, so this is actually called a parallel wear conductivity probe, as the wires are parallel. In a similar fashion, we can have ring conductivity probes also. So, here the wires are parallel, but here what we do, in the wall of the tube we give some parallel plates, okay. So, this is actually, this blue colored thing is actually parallel plate. So, each plate is connected with the wire, okay, and whatever medium is there in between these parallel plates are actually controlling what will be the resistance in between these two open circuits, okay. So, depending on the medium we can also use what type of voltage will be coming from this ring conductivity probe. Now, to give you example, as we know all the flow regimes, this one parallel wear conductivity probe will be very helpful for bubbly flow or slug flow kind of thing, but ring conductivity probe will be very helpful for your annular or core annular or froth flow kind of thing. This will be very helpful. So, let us see that what is the details of the processing circuitry. So, here we will be finding out that we are having few components in the processing circuitry. First one is one wind bridge oscillator. We will be having one Wheatstone bridge also. Probe is connected in one arm of the Wheatstone bridge. Next, for filtering and rectifying, we are having one amplifier and then precision rectifiers over here. So, this is the amplifier section, this is the rectifier section, and finally, here we are having some low pass section, low pass filter section. Okay. So, whatever probe signal we are getting over here, we are doing amplification, rectification, filtration, and finally store that in the computer. Okay. So, this is a typical processing circuitry. As I have told, this will be constructed by electronics. So, this is a typical processing circuitry signal. Okay. Next, let us take some example. Let us say I was discussing about annular pipeline. So, let us say this is the annular zone, we have shown one cross section. So, you see in this typical section, so this is the cross section, this is the front view of the pipeline. So, you can see lots of bubbles, okay, are there in the cross section. Okay. So, this is actually a bubbly flow situation. Now, if you take the signal using electrical conductivity probe, you will be getting a raw signal like this. So, in the abscissa we are having time over here, and in the ordinate we are having the voltage. Okay. So, you can find out a erratic signal like this. Okay. Now, if we go for signal analysis, first one is nothing but I will be using the probability density function. So, this signal we have actually obtained the probability density function. So, you can find out after doing this probability density function, you will be getting a very sharp peak near low voltage, because most of the time the pipeline is occupied by liquid. So, as a result resistance is actually very low. Right. So, as a result you will be finding out a very high peak near the 0 voltage. Okay. The situation actually differs in this case wherever we are having dispersed bubbly flow. You see, in case of dispersed bubbly flow, diameter of the bubbles are smaller compared to this one. Okay. So, here you will be finding out that lots of small bubbles are over there, which probably is not being tackled using your probe. Okay. So, the signal, typical signal will be like this, voltage versus time, and in the same fashion you will be getting a peak also over here near 0, but there are differences between these two peaks. This peak will be very sharp, okay, because we are having small number of bubbles in this case, whereas a very large number of smaller bubbles over here in the dispersed bubbly flow case. Okay. So, this peak will be little bit flattened compared to the bubbly flow peak. Okay. System will be changing whenever we are finding out a slug bubble. Okay. Here you see a typical slug bubble around one annular cross section. So, you see this is the slug bubble, open slug bubble basically. So, you will be finding out the signal is showing lots of peaks and valleys. Okay. And if you go for signal analysis, probability density function, you will be getting two peaks, first peak near the 0 voltage and second peak near 1 voltage. Remember, these voltages we have actually normalized. Okay. So, here you can find out sometime we are having presence of gas whenever we are having contact of the probe with the gaseous phase. So, we will be getting a peak also over here. Okay. And for the liquid contact we are getting the peak somewhere over here. Okay. So, if we see the signal and the probability density function for both the phases, slug flow and your bubbly flow, we can understand that which type of flow regime is occurring inside the pipeline. Similarly, in case of churn flow, as we know, churn flow is very much erratic, there is no fixed configuration in the pipeline. So, we will be getting a signal like this, okay, very erratic flow signal kind of thing, and if you go for the probability density function, you will be finding out no peak at all, right. So, that shows that we are having typically a churn flow or chaotic flow kind of thing inside the pipeline, right. Okay. Next, let us try to go for another experiment where we will be showing simultaneous flow of two miscible liquids. So, this is actually liquid flow, immiscible liquids. So, here we have used both conductivity probe and optical probe. Okay. And we have actually processed the signal for using PDF. Okay. PDF already I have shown you in the previous experiment, and here new thing we have done is actually wavelet. Okay. So, this is single sensor, but multiple features. Okay. So, this is a typical example of the setup. So, here we have used both optical probe as well as your electrical conductivity probe. So, as I have already given you idea of about conductivity probe, let me tell you something about optical probe. So, here let us say this is the pipeline, okay, and here we are having the laser source which will be giving you the light, and on the other hand side of the pipeline we are having one optical receiver which is essentially one photodiode. Okay. Depending on the light intensity coming out of the other side of the pipeline, the photodiode will be energizing and generating some voltage signal, right. So, here schematically I have shown, let us say two liquids we are having water and kerosene, water is white in color and kerosene is blue. So, you can find out the laser light whatever it is giving, some portion is coming in the detector, and detector after energizing it is sending some signal to the processing circuitry via data acquisition system that can be coming to the computer. Okay. So, this is a typical example. So, you can see the processing circuitry over here. Okay. Here we are having the detector, in this side we have the laser source. Okay. Now, as I have told that I will be telling you about wavelet analysis. So, let us see that features of wavelet analysis. So, this is actually a mathematical microscope with adjustable focus. It acts as band pass filter. It is having very good time resolution at high frequency and good frequency resolution at low frequencies. Okay. And we use wavelet to obtain multi resolution. Okay. So, let us show you a typical wavelet analysis. Here this is the raw signal S. So, in this abscissa we are having time, in this ordinate we are having the raw signal. So, you can find out this is the raw signal from your pipeline, liquid flow pipeline. So, what we do, we decompose this signal into one A5 and then D5, D4, D3, D1, D2. Okay. So, all these D's are plotted over here and this A5 is over here. So, this is basically a fifth order wavelet analysis. So, you can go for higher or lower order respectively, you will be getting the equation and the signals. So, here you see this D1 is actually the major signal from here. Okay. So, if you subtract S minus D1 you will be getting D2. Similarly, if you subtract S minus D1 minus D2, you will be getting D3. Something like this, if you continue, finally you will be obtaining A5. Right. Now, after decomposition, what we will be doing for a typical signal, we will be finding out the probability density function or standard deviation for all those D1, D2, D3, D4, D5 and A5 along with the raw signal S. So, you see here along with the conductivity probe signals, we have shown you the optical probe signals also. So, this is a typical signal with respect to time whenever we are having bubbly flow, and we have shown here the probability density function from the conductivity probe signals and D1 A5 from the wavelet analysis and their corresponding standard deviation over here. So, you can see for bubbly flow we will be getting a falling nature of all these intermediate frequency standard deviation. The system changes whenever you are having turbulent flow. So, you can see the PDF was like this for bubbly flow, but for churn turbulent flow PDF is shifting towards 0, but we are not having any difference in the standard deviation of the wavelets. Okay. So, using both the things we can recognize actually the difference between bubbly flow and churn turbulent flow. So, the wavelet analysis is not giving us any difference, but PDF or conductivity probe signal is giving us the difference. Okay. But that will be important whenever optical probe signal will be important in case of coannular flow. In case of coannular flow, you see we can find out the complete reverse nature of the standard deviation of all the wavelets D1, D2, D3, D4, D5. You see earlier it was falling nature, now it is continuously increasing nature. So, using the wavelet we can find out that what is the difference between coannular flow and bubbly flow or your churn turbulent flow. Okay. Similar thing can be seen for dispersed bubbly flow. Here you see the random erratic nature of the signals, okay, standard deviations of all those decompositions. Okay. PDF shows a similar kind of thing, okay, whatever we have seen in case of your electrical conductivity probe. Now, to summarize, in this lecture we have listed down all possible techniques for measurement of two-phase flow void fractions. We have shown construction and working principle for the electrical conductivity probe, and we have also shown you the optical probe construction and working principle. For signal analysis we have shown you the probability density function and wavelet analysis, how those are important for recognizing the flow regime inside a pipeline. Okay. Let us try to test our understanding. So, we are having 3 questions over here. Using electrical conductivity probe for a given signal input, output will be maximum when pipe is occupied by 4 options we are having: complete liquid, complete gas, annular liquid around gas core, and finally answer D is stratified liquid and gas. Okay. So, from the principle of the conductivity probe we can find out that answer will be complete liquid. Okay. Question number 2, for slug flow how many peaks are obtained in probability density function? Okay. So, answers are 1, 2, 3 and 4. Okay. All of you know answer will be 2, right. Next, third question, wavelet analysis gives good time resolution at low frequency, good frequency resolution at low amplitude, good frequency resolution at low amplitude, and finally part D, good time resolution at high frequency. Okay. So, already we have given you the characteristics of wavelet analysis. Please go through that one once again. I think you can get the answer. Last one is the answer, good time resolution at high frequency. With this I will be ending this lecture. Thank you.